This is a University of Otago podcast.
Welcome everyone. My name is Vernon Squire. I'm not the Vice-Chancellor. Harleen Hayne is away today and has tendered an apology, so I'm doing it. I'm the Deputy Vice-Chancellor, Academic and International. These inaugural professorial lectures are very special events in my calendar and hopefully in yours as well. We don't have them every week. We have them every 2 or 3 or 4 weeks. And they're very special events because they're really celebrating the pinnacle of academic performance within the university. In the case tonight, we have what I would refer to as a polymath, someone who has abilities in many areas. Michael obviously is a very able researcher in software engineering, but he's also a very good teacher, and he joined the university originally at the Higher Education Development Centre, where he was in the educational media group. So he has strong interest in teaching. But as well as that, he's a musician, a keen, avid reader. He's a composer. He writes his own music and is very interested in choral work. So he really is a true polymath. He does a bit of everything. Now, the Staffing Advisory Committee, which is the promotions committee of the university, is very keen on polymaths. We like people who excel in lots of different things. And in fact, even our criteria are set out in terms of excelling in research. We expect what we call sustained outstanding competence in research, sustained outstanding competence in teaching, and sustained outstanding competence in service. And on top of that, we expect leadership in 2 of those 3 areas. And Michael has succeeded in achieving that very, very high level of outstanding performance. So it's really with some great pleasure that I am able to introduce the Pro-Vice-Chancellor of Commerce, who'll tell you a little bit more detail about Michael before he begins his inaugural professorial address. So I'll pass over now to George Benwell, who will give you a short biography of Michael's achievements.
Thank you, Vernon. Firstly, thanks to Michael, because I don't think I've ever excited the Staffing Advisory Committee on anything I've ever done. Well done, Michael. Sorry, Vernon. Deputy Vice-Chancellors, academic colleagues, ladies and gentlemen, and the Winikoff family. Professor Michael Winikoff has spent most of his life in Melbourne, Australia. What a wonderful city. An early interest in programming, along with more than a passing interest in mathematics and science, led him to enrol a BSc in computer science at that wonderful institution, slightly less than this one, University of Melbourne. His appetite whetted by summer projects, he decided to go on and do honours, and naturally, as we do, on to do a PhD. After completing his PhD in '97, he worked at the University of Melbourne as a postdoc, moved to the USA for a year at the Institute for Software Research in West Virginia before returning to Melbourne to take up a postdoc at RMIT University. In 2000, Michael was headhunted by a former and fellow student and left academia for that seductive corporate world and developed a public transport information system known as Smart Guide. I'll leave it to Michael later, hopefully, to explain whether that was a success or not, because less than a year later, he was allured back into academia. And Michael returned to RMIT in 2001 as a postdoc, then transitioned to a lecturing position, and then to become an associate professor in 2007. So that's a fairly meteoric rise in academia from a lecturer to associate professor within 6 years. In 2008, Michael took a sabbatical and came to Dunedin for a few months. It's fairly obvious, but true. that he and his family are still here. He caught the same bug that I did. Deciding to remain in Dunedin, Michael found a position at HEDC, which the Deputy Vice-Chancellor has referred to. A year later, Michael joined the Department of Information Science in the Division of Commerce and took on the role of the head of that department early in 2011. Outside academia, Michael is an avid reader, an even more avid musician, singing in the Southern Concert of Voices. Michael is also known widely as a pianist, accompanist, and has the ability to assemble, I'd like to say ensembles, but it says medleys, of incongruous themes, as all software engineers do. One medley combining Harry Potter, Lord of the Rings, Star Wars, Shrek, amongst others. He holds an A piano, and in his spare time, which you wouldn't imagine there'd be any of, he composes primarily for choir, with works having been performed in Australia, the UK, the US, and of course, New Zealand. Human-inspired metaphors for software. It's been said that software runs the world, or if it hasn't, I just did. Although the techniques that are used to design and build software have advanced enormously since 1968, when the term software engineering was coined, the dominant metaphor, the paradigm that we have all used, has continued to view computer programming as a sequence of instructions, one following the other. However, using this metaphor yields software that I would argue may cope poorly, doesn't necessarily, but may cope poorly with the complexities of the real world, where there are often multiple paths to achieve given outcomes, and where things can and obviously do go wrong. This has prompted work on alternative metaphors for software, including one inspired by humans that make decisions in the complex world we live in. For example, instead of viewing software as a sequence of instructions, we can view it as a collection of goals to be achieved, along with a library of plans that can be used to achieve these goals in different circumstances. Professor Winikoff's work over the last 15 years has been in this space. He has focused on how-to aspects, on how can engineers design and build software that is based on human-inspired metaphors, such as goals and plans. His work has resulted in numerous papers, a book, an award-winning supporting software tool, and collaborations with industry. He has excellence in academia and relevance in business. Colleagues, it gives me the greatest of pleasure to ask Professor Michael Winikoff to present his inaugural professorial lecture entitled Human-Inspired Metaphors for Software. Michael Winikoff, Professor.
Thank you very much. Tēnā koutou katoa, good evening, and thank you for taking time out of your busy schedules to be here tonight. Now, can I quick show of hands, who here uses software? Okay. My first point is that software is everywhere. I was going to have a slide that looked at the different sorts of software, how it's not just what you see on your laptops and desktops and tablets and phones, it's also the embedded software in cars and planes, and it's also the software that's used in the infrastructure, things like electricity distribution, supply chains that make sure that there's stock on shelves and so on. But I found an alternative way to argue that software really is everywhere. If you read that sticker, it says peel, play and win, and if you peel it, you find a QR code that takes you to an app. So if a banana comes with software, then software truly is everywhere. As George highlighted, the sort of overview of what I'll be talking about tonight is human-inspired metaphors for software development. So my first point is that software is indeed everywhere. The next point is that software is based on metaphor, and I'll elaborate shortly. But more importantly, the choice of the metaphor matters, and specifically the traditional dominant metaphor that views a computation or a program as a sequence of steps copes very poorly with certain situations. So what do you do about that? You look for alternative metaphors. And in particular, in doing so, we can draw inspiration from humans, human organisations, and human societies. The key questions then are, what sort of metaphors can we draw, and then how do we actually realise these in software? What does it mean to take an inspiration of, say, human decision-making and realise that in software? So that's the first key question. And the second key question is, once you've done that, how do you guide software designers and developers to use these features so that they reap the benefits of those features? And at the end of the talk, I'll change direction a little bit and talk briefly, literally 2 slides, about technology, universities, and disruption. So software development is based on a metaphor. Software is developed by writing programs in programming languages. Different programming languages are very different to each other, but they're all based on some underlying metaphor or vision, the technical word is paradigm, for what does computation look like. And in fact, the vast majority of commonly used programming languages are based on the same underlying metaphor of a program is a sequence of instructions where you execute or perform one instruction and then move on to the next one. So that's where we stand. Why is that a problem? It's a problem because for certain situations where things can and do go wrong, not just in easily anticipated places where you might be able to check, but at any point along the way. Or if you have multiple ways of achieving a desired outcome. Or if you're dealing with humans, perhaps as part of a business process, and you want to model flexibility. So there might be a number of steps, and perhaps step 5 can come before step 4 under some situations, and maybe step 2 is optional. How do you model that? And it turns out that if your programming language, if your way of thinking is based on a rigid sequence of steps that's strictly followed, then it's quite unnatural and awkward to model these sorts of situations. To make it a little bit more concrete, here's an example. The details here aren't that crucial. This is the sequence of possible steps, of possible sequences that can occur in an interaction. And the key point is that this is an interaction that involves 6 steps. And there's some degree of flexibility, so you want to allow for things to occur in slightly different orders, and when you expand it all out, this is what the interaction looks like in this example. So if you can imagine trying to capture this using a program that says, well, you do step 1 and then you can either do step 2, and then if you do step 2, then you can either do step 3, but maybe you can do step 4, it very quickly becomes a rather of a mess. Even worse is somebody comes along a little bit later and says, you know what, yep, that looks fine, but let's add another step, a step 7. And that can go either at the end, or it can go before step 4, or maybe you can replace it with an alternative. So this is the sort of situation where you want to model flexibility to support humans doing things in the way that we like to do it, perhaps, or that the domain actually requires things to be done in different orders, and it doesn't work in an approach that's based on a rigid sequence of steps. So that's the problem. What then is the solution? The solution is to look at an example of a system that deals very well with things going wrong, that deals very well with flexibility and doing things in different orders, namely us. Humans, human organisations and human societies deal very well with these sorts of issues, so it's a fairly natural thing to look at humans, organisations and societies for inspiration. Now, on the bottom there I say metaphors, and that's intentional because there are a number of different metaphors that can be drawn by looking at these different aspects. So if you look, say, at human societies, you might be inspired to look at computational or software metaphors that revolve around laws or norms or incentives. And that part of the community has a lot more to do with the economical paradigm and with ideas from economics. And the idea there is if you have a collection of self-interested entities, be they human or software, how can you design incentives and mechanisms that ensure that the society as a whole functions well despite people being able to operate in their own self-interest? Or if you look at organisations, human organisations, how do they negotiate? How do they coordinate? Again, there are mechanisms there that we can abstract, model in software and use usefully to solve problems. In today's talk, I'll be focusing mostly on metaphors that we gain or are inspired by looking at individual humans. How do we make decisions? How do we act? How do we adapt when things change or when things fail? And one reason for focusing on that is that that's where most of my work has been. The other reason I'll come back to on the very last slide. I'll explain that there. So if I focus on humans, how do we make decisions? How do we cope with things going wrong, with things changing? Well, one possible metaphor that you could look at is inspired by this idea of goals and plans. So a software entity has a collection of goals that it's trying to achieve and a library of plans that it can use to achieve those goals. An important point here is that goals are persistent. So if I have a goal to do something and I hit a setback, something goes wrong, I don't drop it, I keep on trying. I find an alternative way of doing things. So let me give you an example to illustrate, and this is an artificial example. Imagine that I have the goal of going home, and I have a number of plans I can use to do that. So if it's nice weather, I could walk. If it's raining, I could catch the bus, and so on. Catching the bus is itself a somewhat complicated process. It involves a sub-goal that then has a plan that can be used. So this is obviously a simple example. I've got 2 goals and 4 plans. What does this actually do? What sort of behaviours can I get out of these goals and plans? Well, suppose that I try and actually enact this and go home. The first thing I need to do is to consider, okay, I have this goal, which of the 3 possible plans could I use, and then which one would I use? Let's imagine it's currently raining, so the first plan is ruled out, but the other 2 are possible. And suppose that I pick the second one. At this point, I'll have a goal, or perhaps a sub-goal, of catching the bus, and there's only one plan that can be used, so I'll go ahead and pick that one. I'll walk to the bus station, I'll check the timetable to see whether the bus is imminent, and if it is, then I'll wait and eventually board the bus. In this case, though, I find when I get to the bus station that I've just missed a bus and the next one isn't for quite a while. So at this point, that plan fails. What then happens? Because the plan has failed, the goal that it's trying to achieve gets reconsidered, and since there's no other way to catch a bus, that fails as well, which then means that my plan of getting home by catching the bus has failed. Now, at this point, I've tried to go home by catching a bus, that hasn't worked. Now what happens is I try alternatives. So that plan's been tried and failed. What about the other plans? This being Dunedin, where the weather changes frequently, it's now sunny. So the remaining 2 plans are both applicable, and let's say I pick the first one. So the point here is to illustrate that using this simple example, goals and plans can lead to behaviours where there is flexibility in how I do things, where I can pick between alternative pathways based on the circumstances, and where if something goes wrong, I can recover from that by looking at alternative plans and picking between them. So this is a fairly small set of goals and plans, 4 plans, 2 goals, and this is just one of the possible behaviours that it can produce. It can produce a whole range of other possible behaviours. So the other point here is that goals and plans provide a way of expressing many possible behaviours, and they provide a way of doing this that's quite compact. So this is a sort of the intuition of how goals and plans might work, but is this actually of any use to anyone? Yes. So this is a quote from a paper, 2006 paper, written by a bunch of people from a commercial company called Agentis. Agentis is a company who made their living developing large-scale software systems for paying customers in a range of domains: finance, insurance, logistics, energy, and so on. And they say that in a wide range of complex business applications, the use of this technology, BDI is the technical term for this idea of goals and plans, provides a significant improvement in developer productivity. Now, the bad news is that these are people who have the experience to make these sorts of claims. They've developed real systems, they've collected data. The bad news is that this claim is made in a shortish paper and they don't provide the data. They just say that they have it. So you have to take this with perhaps a little bit of a grain of salt. But what I would argue, though, is that this claim is plausible, not because this technology is absolutely brilliant and improves developer productivity by 350 or 500%, but because the conventional approach to developing software that's focused on sequences of steps that are rigidly described is a very poor match for these sorts of domains. So if you're doing work in, say, insurance and you have a process to follow, but there's all sorts of flexibilities depending on what order things are done in, depending on the jurisdiction, depending on the history that you want to perhaps do things differently, then as we saw with that 6-step process, trying to model it using a sequence of instructions using a traditional approach becomes very cumbersome, hard to build and even harder to modify, whereas this approach works quite naturally and quite nicely for those sorts of things. So that's why those claims, with the grain of salt, I would still regard them as being plausible. More broadly, there are many applications of human-inspired software, where here I'm talking about not just being inspired by individual humans, but also by human organisations and human societies. And a lot of the applications where these technologies are useful tend to have these sorts of characteristics, where there's either a need to be flexible, a need to be robust, or perhaps natural distribution and a need to deal with independent entities. So a couple of examples. The decision-making of unmanned aerial vehicles is a fairly natural application for these things, where you have goals you're trying to achieve and you need to adapt and change what you're doing depending on circumstances and on things going wrong. Another area that's seen a lot of interest in recent years is the smart grid and managing energy. So one example there is demand. If you have a whole bunch of independent households who have their own electricity demand profiles, how can they negotiate to coordinate and reduce and smooth out peaks? So that's a question of coordination, negotiation, and perhaps also designing appropriate incentives. I've talked about things like finance and insurance, or mentioned them on the previous slide, and there are also a lot of applications in health to do with the process that you follow. If you're caring for patients, it's not a rigid, you must do A then B. Often there are variations and options that you want to be able to model. So in this roughly first half of the talk, I've argued that software is everywhere. Remember those bananas? I've argued that software is based on a metaphor and that the choice of metaphor matters, and that the traditional dominant metaphor of it's a sequence of instructions works very poorly for certain types of applications. And for those types of applications, we can develop alternative metaphors by drawing inspiration from humans, human organisations and human societies. The key questions then are, well, what sorts of metaphors? And we've seen a hint of one of those. But then how do you realise them in software, and how do you guide design? And those how questions is where my contribution and my work over the past 15 or so years has been situated. So the first thing you have to look at is, okay, you have this perhaps high-level inspired vision of I'm going to write software that is based on how humans make decisions. Well, in order to actually do that, you need to flesh out a lot more detail. What do we mean? What's the sort of reasoning cycle? How do you represent that? What information needs to be specified? What's the behaviour of these things in software? So early work that we did, in this case we being Lynn Padgham, James Harland and myself, back in about 2001, is we said, okay, what concepts do you need for this particular metaphor? And we identified a number of those, actions, percepts and so on. And it turns out that most of those are fairly straightforward to work out what they mean and how you model them. The two interesting ones are, unsurprisingly perhaps, goals and plans. So the next step is, well, okay, what does a goal mean if you want to model it in software? What pieces of information do you need to associate with each goal? What are the semantics of goals? How do they behave? So this is the formal semantics for a programming language that includes goals and plans. Now, I'm not going to talk through the details, but where does this come from is perhaps more interesting. So the motivation here is that, as we've seen earlier, goals need to be persistent. If something goes wrong, you want to keep on trying. What that then means is you should not drop a goal unless there's very good reason. So what are those good reasons? Well, we identified that the two situations where you can and should drop a goal are when it's achieved, So a goal should be unachieved. Once it's achieved, you drop it. And a goal should be possible. If it becomes impossible to achieve, that's when you can and should drop it. And that then suggests that two of the crucial bits of information that goals should have associated with them are a condition of when do I deem this goal to be achieved, and another condition that says when do I deem this goal to be impossible to achieve. We also want goals to be known, which just basically means that the piece of software has to keep track of what goals it has. That's fairly straightforward. And one reason for that is because you want the goals to not interfere with each other. And there's literally a whole PhD thesis in that word consistent. That was John Thangaraj's PhD thesis that Lynn and I supervised. And in 30 seconds, the idea there is if a software entity has two goals and it's running plans and going through that process, you need to have algorithms that detect when following this goal and doing some steps might interfere with what you're doing over there. And there's a whole contribution there of how do you do that and what are the algorithms and the steps and the data structures and so on. Then there's this idea of a goal life cycle. So once a goal is activated, adopted and activated, then there's a process of identifying plans that can be used, executing those plans, enacting them, and then repeating that until the goal is either achieved or deemed impossible. So that is the question of how do you embed these ideas in software? What additional details do you need? And the outcome of this sort of process is a programming language that provides features like goals and plans. The next key question is how do you guide developers to use these features effectively so they reap the benefits? Now, the experience both of Lynn Padgham at RMIT and elsewhere, other people elsewhere, was that you need guidance in doing this. You need a methodology. So the early experience that Lynn had, this was somewhat before I joined the team, was that you take some of these ideas, you get postgraduate students and you give them a platform that provides these sorts of features, give them an appropriate problem and say, right, design and build a piece of software. They struggle, and the result is not a good design. It tends to have a small number of plans where each plan is very long, so there's no opportunity to recover or to do things flexibly. So there really is a need for a methodology. So what is a methodology? It's a guidance for how do you go about designing software. Now, at the highest level, it's a process, and this is a high-level picture of the Prometheus process. Now, for those of you who are not familiar with software and how it's designed and built, a metaphor here is storyboarding with movies. So if you're going to shoot a movie, you don't perhaps, and especially if it's a movie that's unfamiliar or has new elements to it in terms of the type of movie or the style of movie making, you probably won't start off by putting actors in front of the camera. You'll start off by storyboarding it. And a storyboard is an abstract model of certain aspects of the movie that allows you to assess things like how does the sequencing of scenes work, what are the camera angles I'm going to use, and a whole bunch of other things. So it's an abstract design. And similarly here, the design process in software develops artifacts, often structured and graphical, that capture certain key aspects of the software, the structure of the software, the information that needs to be manipulated and retained, and the behaviour of the software. So methodology is a process. It guides people in where do I start, what do I do first. But most importantly, this picture there, that's the process. That's one page in the book that Lynn and I wrote. The other 200 odd pages are the rest of it, which is not just the process. Okay, step one, you might need to identify the scenarios, but how do you do that? What does the resulting scenario look like? What notation do you use to capture them? And what are the techniques you can use to identify the scenarios? Now, software design, a little bit like movie making, is not an automated process where you can turn a handle or follow a strict routine and get a result. It's a creative endeavour where often there's not a single right answer, but a whole bunch of plausible answers. So methodology can't be here's a process you follow to the letter and that's all there is to it. Instead, what it can do is provide guidance, heuristics, rules of thumb, and questions that you can ask to guide the designer in identifying appropriate trade-offs and identifying appropriate features. So the Prometheus methodology has a lot of detail around that. How do I perform the different steps? What are the results and guidance and heuristics and so on? Now, it's quite detailed, and what I would say is that developing methodology is actually easy. Developing a good one is what's really hard. And the Prometheus methodology, I would argue, is a good one. It evolved over a number of years out of experience both with collaborating with industry and in teaching this. You'll recall that the motivation was a situation where postgraduate students were struggling. With the methodology in place and with some degree of refinement and development, Lynn and I were able to teach these ideas to undergraduate second-year students and have them successfully design and build simple agent systems, simple systems using these ideas. So that's the sort of left-hand side of the slide, the sort of how do we embed this in software and then how do we guide people to use it appropriately. The next few slides, what I'd like to do is to very briefly look at 3 papers that I've done, and I've picked these 3 for a number of reasons, but one of them is that they exemplify some of the different research methodologies. And one of the things that I find really enjoyable is that in the process of doing research, I get to do all sorts of different methodologies. So one paper might involve human participant experiments, another piece of work might be very mathematical in nature. So you get a diversity there. So this is a paper that Hoa and I did back in 2003. Now, back in the early 2000s, there was general sense in this community that we needed methodologies. And then what happened? Every person and their dog proposed methodology. There were dozens of these things. Not quite every person, but there were quite a number. And the natural response to that was, we've got all these methodologies. How do we know which ones are good? How do we know which ones to use? Let's compare them. So then there were a whole body of work that looked at take some methodologies and compare them. The approach they tended to adopt, almost without fail, is what I'd call the big table approach. So all of these papers, every single one of them has a big table where there's some list of criteria that they came up with, and then there's a list of methodologies, and for each methodology and each criteria, the author typically had read the papers in that methodology, looked at the criteria and said, well, the MACE methodology, how well does that support reactivity? Medium, high, low, medium. There's 2 problems with that. One problem is, where do these criteria come from? And they need to be well motivated, justified, and ideally reasonably complete. That's not too hard to solve. That's a relatively minor problem. The bigger problem is that every cell in this table is subjective. So, and indeed, every single paper pretty much of this sort that I've read has had some entries in the table where I've looked at it and gone, I don't quite agree with that. I mean, maybe MACE should be high rather than medium on that criteria. The other issue is that by and large, the people who write these papers will have read the papers on the other methodologies, but they won't have used them. And indeed, finding time to do sensible design projects with 3 or 4 methodologies is quite difficult. So they won't have used those methodologies, which means they're not well informed. And maybe not every, most of these papers that I've looked at have had a cell somewhere in the table where I've looked at it and gone, it's not just that I don't agree with that, I think that's very clearly wrong. So what Hoa and I did to try and improve the state of things was, well, we derived the criteria based on existing work and other stuff, which I won't go into, but we dealt with this issue of being subjective and being not well informed by having a bunch of summer students who each did a project and each used a different methodology. So they were then well informed about that methodology and they completed their own assessment of that particular methodology. We also did a survey of the authors of each of the methodologies to get the sort of real experts who may be biased but gives you a sense of where they're coming from. Each cell in that table where you see multiple letters separated by a slash indicates that there was disagreement. In some cases, we found that where methodology had been created by 2 people, they disagreed with each other about whether support for X was strong or highly strong or agreed or strongly agreed. And some aspects of this work were quite influential in sort of subsequent how people did evaluations and comparisons. Another example, another paper, more recent one, is work with Chris Cheong, who's a former PhD student of mine, and this came out of his PhD thesis. So this was about the question of how do you design flexible interactions. Now, all of these sorts of methodologies have a way of designing interactions, and To be honest, none of them do a really good job. They all tend to use fairly similar ideas, including Prometheus, and they're not great. They're adequate, but not great. So Chris, in his PhD, developed a new way of doing things that was hopefully an improvement. How do we know if it's really an improvement? We do a study. So we got a bunch of people, gave them a scenario and said, design me the interaction protocol, and then we got those interaction protocols back and we assessed them on a whole bunch of criteria. This table is just one of those criteria, and it shows that, so for this criteria, the idea was the scenario has a certain number of steps, and you want the resulting interaction protocol to actually cover all of those steps for it to be correct. About half of the people who'd used Prometheus missed out on at least some steps. Every single person who used Hermes covered all of the steps. So that's showing that there's an advantage to Hermes with respect to this criteria. But the other bigger point here is that what this shows is that the choice of methodology matters. So in this case, where you're comparing a methodology that's okay with another one that aims to improve it, and we see a significant difference. That provides empirical support for the anecdotal evidence that Lynn and I were seeing, that having a methodology in the first place made a big difference to people's ability to design software that used these features. A third piece of work that's even more recent, hot off the press. You might recall earlier on that I said that goal plans allow us to represent many behaviours in a compact way. So this paper sets out to answer the question of what do we mean by many? Can we quantify that? And this is not just an academic exercise, it's actually an important question which relates to testability. If you have software that someone's built, you probably want to convince yourself that it will do the right thing before you deploy it. And traditionally, the standard way to do that is to test it. You get a whole bunch of different situations, run them through the software and see if it does the right thing. The ability to do that depends on how many different behaviours the software can exhibit. If there's a large number of structurally distinct possible behaviours, then the number of tests that you need also becomes quite large. And if there's a really large number of possible behaviours that are structurally distinct, then you can't get confidence that it'll do the right thing by testing it, because that would require just way too many tests. So Stephen and I did this is an example of a mathematical analysis where we derived mathematical equations for the number of behaviours in a given collection of plans and goals, and there was a whole bunch of things that we looked at around how do you deal with failure handling, how does that affect the numbers, what is the probability of failure, what happens if you look at different rates of failure, what happens if you extend this to infinite trees. And we also did a reality check by running some example programs with a real programming language to check that our equations were correct, and looking at a set of goals and plans from a real industrial application to get a sense of the examples that we're looking at, how big are they and how big would a real example look like. So the conclusion is that many is really lots with capital letters. So to quantify that, that top row there says that for the case where you have a fairly small number of goals and plans, about 20 goals and 40 plans, these numbers are sort of billions. They're sort of Sagan-like numbers. If you move to sort of hundreds of goals and associated plans, then they become truly astronomical. And this has implications for the ongoing research and the need to develop alternative ways of getting confidence that these systems will work that don't rely on testing. Now, George mentioned that I've been involved in collaborations with industry along the way, and there have been a number of these collaborations. I won't go into them in a lot of detail. Agent-Oriented Software is a company headquartered in Melbourne, and Lynn and I had close collaborations with them over a number of years. They supported our early work on Prometheus. We had a project with the Bureau of Meteorology where they were developing together with us a prototype scalable weather alert system, where by scalable we mean it's easy to add in new sources of information and adapt the system. And after moving to New Zealand, Stephen and I and colleagues up in Canterbury, as well as colleagues from overseas, had a project with Jade Software up in Christchurch that was around how do you improve and optimise the unloading and loading of ships. So if you have containers and large cranes and they're moving around like they do at Port Chalmers, how do you improve the performance of that? And also, how do you make them more robust? So if things go wrong, can you help there? Now, okay. So I'll change directions now a little bit. and look at technology, universities and disruption. So this is where I have a bit of a soapbox and a chance to rant for a bit. No, seriously. First of all, though, a disclaimer. This is not an area where I can claim to be an expert. I've not done years of study and published dozens of papers. However, as Vernon and George hinted at, I do have a little bit of a background that's relevant to this, including obviously being an academic, doing teaching, being an academic leader and manager, being a technologist, and also having spent a little bit of time and done a little bit of research on technology and how it applies to education. If you read some of the articles in the press, you can see some rather hyped up comments. And if you read these and read these uncritically, you might be left with the impression that universities are under dire threat from technology and that the internet is going to revolutionise everything and make us obsolete. Language like there's a tsunami coming, a storm's brewing, poised to wreak havoc. There's some really strong words there. So, quick show of hands, how many people here have heard of MOOCs, Massive Open Online Courses? Okay. Majority. MOOCs were, so for those who haven't, there were a few hands, the idea there is that you're offering a course online and the open bit gets blurred. That's about sort of the resources being open that anyone can sign up. The course refers to the notion that it's not just lectures that you can view, there's also work that you do, assignments and questionnaires. The massive, though, refers to the fact that there's no direct interaction with the teacher. So one lecturer can serve tens of thousands of students. How does that work? Well, there's no way of communicating back to the lecturer. They'd get swamped if there was. And any assignment that you do either has to be automatically graded, so perhaps a multiple choice question or a software program that can be run and automatically given a mark, or it gets evaluated by your peers. So that's the massive bit. MOOCs were very much flavour of the year a couple of years ago. There was enormous amount of interest and hype, and it seems to have died down and turned around surprisingly quickly. So some of my comments are specific to MOOCs, some are more general. So what I don't have here is answers. I don't have a crystal ball. I can't predict what will happen 2, 5 or 10 years from now. But what I do have is questions. So next time you read an article about the latest technology that's poised to revolutionise everything about education, you can ask some of these questions and hopefully come up with a better sense of, is there really something here or is it just being overhyped? So the first question is it relevant to New Zealand or is it focused on the US? Why does this matter? Because disruption is not just about technology, it's also about business models and regulatory environments. And the US environment is quite different to the New Zealand one. And I lose track of the number of articles that I've read that have headlines like university system or there's a storm brewing in higher education, the one we saw in the previous slide. And when you look at it, you realise, oh, it's really talking about US. So doesn't mean it's not applicable, but you need to interpret. And Grant would never forgive me if I didn't say this. If you look at that infographic, it's wrong. The numbers, you probably can't read them. Oh, you can. The first number there is about 9,000. The second one is 12,000, 15,000, 21,000. If you looked at the bars, what would you think the relationship was? They've added a few extra dollar bills along the way. The last one shouldn't be anywhere near that tall. Sorry, that was a pet rant. Had to get out the way. Second question to ask, is it about today's universities and does it overly focus on lecturing? If you go back to the previous slide, the analogy here, the argument why universities are poised to be disrupted hinges on an analogy with the music industry, with newspaper publishing. Some of the text there talks about offering the same educational content. So it's focused on universities as being about information dissemination. The sort of vision that universities, well, that's where students sit in lectures, academics talk at them, throw information out, and then students get examined at the end. Now, I realise there's variation between disciplines, and maybe that is still the case in some disciplines, but it's not the case in computing. It wasn't the case in computing when I was an undergraduate. So there was a TV series recently where Nigel Latter went in one episode into schools, primary and secondary, and he found that the way children were being taught today was vastly different to the way that he had been educated a few decades earlier. So some of these articles that argue that universities are just about information dissemination and information is now free on the internet are perhaps based on an outdated or naive view of what universities are. Does the proposal generalise to all students, to all disciplines? This is a little bit more focused on MOOCs. There was initial enthusiasm with MOOCs where people were making claims like, I offered this course, I had thousands and thousands of students, I gave them the same exam I gave my normal face-to-face students and they did well. Therefore, MOOCs work. No, you have to look at the samples here. The MOOC audience is incredibly biased, incredibly non-representative. They were the early adopters. And we know that because there have been some studies that have looked at these audiences and they've shown things like the vast majority of people doing these MOOCs already have degrees. A significant proportion of them have postgraduate degrees. There was a case with a course at MIT where some of the students doing this course online as a MOOC had done the real course at MIT. So these are MIT students, current or former. It's an incredibly selective audience. So the real question is, for MOOCs to be a revolutionary threat to universities, would it work if I hypothetically proposed to get rid of Business 106 and replace it with a MOOC? And from everything that we know about the role of the teacher, how students learn and who that cohort is, I can tell you it would be an unmitigated disaster. So would they generalise to all students? Would they generalise beyond the initial carefully self-selecting and highly enthusiastic sample? Probably not. Would they generalise to all disciplines? You can envision that certain topics in economics or in mathematics or physics might lend themselves to being put online and taught in this way, where you watch lectures and discuss things and answer quizzes. What about other topics, lab-based things like the lab-based aspects of physics or chemistry or anything to do with health science? So certain disciplines don't lend themselves at all to this sort of model. Is the proposal financially sustainable? Now, MOOCs often have the word free associated with them, and that's somewhat misleading. They're offered and they're free to the student, they're not free to the institution that creates them. It takes tens of thousands of dollars to create one course. So if you have initial seed funding, then that works, but it's not sustainable. Of course, if you're an institution like Stanford, then Stanford could be described as a large investment bank with a small university attached. They're sitting on, $17 billion of endowment funding. They can afford to spend $30,000 to create a MOOC, and that becomes advertising. And I realise we're a bit short on time, so I'll skip those last 2 points. So there's a saying that it takes a village to raise a child. And there probably should be an equivalent saying that it takes a village to raise an academic. Forgot that. If I leave you with one thought about this whole idea of revolutionising things in MOOCs, it's been argued that MOOCs will revolutionise education because they're free. An analogy would be that, if this thing behaves itself, that walking will revolutionise transport because it's free. And the argument here is that walking has its place, but it's fit for some things, not for others. Just because something is free doesn't mean it will revolutionise everything. It depends on whether it's fit for purpose and for what purposes it's fit for. MOOCs have potentially a good place in lifelong learning. Once somebody's got degrees, they know how to learn, it's a good resource. But as a replacement for undergraduate teaching, I'm pretty confident in saying it will be a disaster. So, coming back to my point about taking a village to raise an academic, I'd like to thank all the people that I've worked with along the years. So this is hopefully a list where I haven't left too many people out. It's basically a list of those people that I've collaborated with and that has resulted in a publication. Now, there are a few people that I'd like to thank specifically, so special mentions. Harold Søndergaard was the person who got me involved in a summer studentship a number of years ago. He then went on to supervise my honours thesis, and James Harland and Harold Søndergaard were the co-supervisors for my PhD. So they're the people who got me started on this journey. Lynn Padgham is a close colleague at RMIT. She hired me. She was for many years my boss. We're also close collaborators. We continue to collaborate. And she also has been not just a boss and a collaborator, but also a friend and a mentor. And I've learned enormous amounts from working with her and from interacting with her. So I'd like to take this opportunity to thank Lynn for everything she's done over the years. And last, but absolutely by no means least, my family. So I'd like to thank my family for all the support, the encouragement, the patience and the tolerance and the putting up with me over the years. And in particular, my wife and my kids were hiding out the back with their iPads. So thank you very much. Yes, that's you. And my parents. So my mother, who's not able to be here tonight because Melbourne is a fair way away. And as George mentioned, I sort of came here from Melbourne, which was a very intelligent and wise move. And George should know, having done that himself a number of years earlier. And finally, my father, who's not able to be here because sadly he passed away a few years ago. And I know that if he was still alive, he'd be absolutely thrilled to be here tonight. And I'd like to end with a plug, an advertisement. So every year, a number of people at the university are promoted to professors. It's a relatively small number, typically 20. So it's probably unusual, and Vernon can comment, to have two people in the same department be promoted in the same round. It's probably even more unusual for those two people to be collaborators. So I was absolutely delighted that Stephen Cranefield was promoted to professor, and I would encourage you to keep your eyes open for his inaugural professorial lecture. So Stephen's an RSL, so it's not happening this year, but it will happen next year. Date to be determined, and please do come along to that. And finally, again, thank you very much for taking the time to be here tonight.
Good evening. My name's David Fielding. I'm a professor in the economics department. This is the slot that would usually be filled by a head of department talking about the professor, but Michael is a head of department, so that's why I'm standing up now. So this is an outsider's view on what Michael has been talking about. And talking to Michael and one or two other people in the information science department, and also listening to his talk tonight, it's really changed my view of information scientists and computer scientists. I used to think that to be good at computer science or information science, you just had to be good at maths. And as you saw from some of the slides, that's probably still true. You do have to be pretty good at maths to do some of this stuff. But what Michael's really impressed on us tonight is that you also have to understand people, and you have to understand how society works as well. And that's where the polymath part comes in. It's in the interaction between the understanding of the engineering and the mathematics and how that combines with understanding people. And Michael's shown that to make computers and software relevant to the world, you need to be good at both of those sides of the business. And that's where Michael's been really successful indeed, both in academia and also in the practical applications. I would just like to mention one thing that Michael's not talked about at all. Michael is an enormously good citizen within the university. He's been a very young head of department. I sit with him in very many committee meetings. While others are losing their head, Michael is always calm, collected, and logical, as you would expect of someone in his discipline. He makes an enormous contribution in different ways around the university and also within the division. And the university is very fortunate indeed that he's with us. So will you please join me again in thanking Michael? And Michael, would you stand up? So this is just a small token to recognise this occasion. Michael, thank you.
Thank you.